So injective aggregator is defined in many different shapes. For your understanding, the injective function means that when we say the function f from x to y is injective if the function f maps different elements to different output. When they have the different output, it maps onto the different element in the output space. So from this assumption, we can get the intuition that the app retains all the information about the input. When it has all the information, it is able to generate the map onto the y with the different elements. That's why we are able to say it retains all the information about the input. In the injective aggregator, so we have learned about many different aggregators in the GCN and GraphSage. The GraphSage introduced 3 different aggregators in mean pooling and max pooling and LSTM that based the aggregator. Here they compared 3 different aggregators. First one is the max pooling and in mean pooling and some multi-set aggregator. So they compared each aggregator's the expressive power. They were able to show that the max and mean aggregators are not that powerful compared to the sum multiset aggregator. So let me show you one by one. And they try to say the GNN is, you should be able to represent the subtrees injectively in the output embedding space. The injective aggregator is able to map the different subgraphs onto the embedding space with the different outputs. So that is what they want to show in the paper. And let me show you the injective aggregators. So from the simplest form could be found in the GCN, right? When you all understand what the mean pool means. So it takes the element-wise mean and followed by linear function and Lambda function. And when you see the paper, I remember that is in the first or second. So their theorem say that the GCN's aggregation function cannot distinguish different multi-sets with the same color proportion. Here we have discrete the features per node, and when some nodes, we have a node and it has different neighbors. So some node has this neighbor, some node has these 4 neighbors. They all have different the feature sets. So when we use mean pooling, we're not able to distinguish the 2 sets, right? For example, we can represent each feature as one hot representation. So we have two different possible features, and we can use one-hot representation with this. We try to leverage the mean pool for the isomorphism test. And where we go through, take the one-hot encoding from the two different sets. When we take the element-wise mean pool, we get this and this. When we use all the set-wise information, when we go through the linear and Laplace function, we will get the same output, which means we are failed to distinguish two different neighbors. Now, that is a problem. And what about the max pool? So we are not able to then distinguish the three different inputs. So graph is aggregation function. So they take the maximum value to aggregate the neighbors, right? Similarly, we have the one-hot representation. So now we use an MLP for simplicity, and we have this and this and this. What if we get the element-wise max pool? We get this and this. We get, because this is element-wise max pool. At the first axis, we take the maximum value, and we are able to get this. Similarly, we look at the axis. We take one, we take one, we take one, we take one. So they all are the same, which means it fails. So the findings are summarized in this slide. The expressive power of GNNs can be characterized by that of the neighbor aggregation function. And neighbor aggregation is a function over multi-sets. We also assume that sets with the repeating elements. And Gaussians and Gaussian aggregation functions fail to distinguish some Bayesian multisets, and the failure means they are not injective. And therefore, the Gaussian and Gaussians are not maximally powerful GNNs. And hence they are not able to include the neighbors, and they are not injective, the aggregator. So we try to solve, and at least to try to include the previous failure cases by proposing a new inductive aggregator. In the theorem, they try to say that when we follow this multi-set function, we follow this form, we are able to identify, we're able to pass the failure cases. It still looks very familiar, right? So, but difference is we sum over multi-sets, and we take some function toward the node feature. So from this input, we need to design the function app per node, and we need to have another nonlinear function to take the sum of the function output. So this is the difference. So how would you prove that? So this is the illustration of the proof of the theorem. We assume that the app produces one hot encodings of color. So we assume this in the second aggregate example. So when the app produces one hot encoding, and when we sum all the information like this, and we are able to pass the previous failure cases. So different from just pure the mean pooling or the max pooling, we summed over the outputs of the neighbors, where we get the final output from the nonlinear function. So we are able to get the expressive power of the isomorphism test, the WL1. So but we haven't talked about how this is related to the WL1. So for your information, so this f and the pi, and we can use any multi-layered perceptron. So in theory, to prove this, we use a universal approximation theorem. So we can say one hidden layer with a sufficiently large hidden dimensionality and nonlinearity activation function, and the layer can approximate any continuous function, right? This is the very famous universal approximation function. So thanks to the universal approximation theorem, so we can prove this. So this is the inductive multiset function. And now we can conclude this. So this is the summarization about their proposed the graph neural network. They call this is the graph isomorphism network. Just apply MLP, element-wise sum, and MLP. So that is their contribution. And in their actual presentation about this is presented here like this. MAP goes to here, and the summation goes to here, and here MLP just simply use the LH, and additionally we consider differently deal with the self-node representation by introducing the eta. And the reason why we use the eta here is that we needed to show each pair of the self-node and the neighbors for each pair, and the HVK should have a unique value. So this makes the injective capability, right? The property for the aggregator. So it is to give the injective the property, and this column 96 of the paper shows why we need this. So anyway, looks very simple difference. from the GCN and graph stage. So by having this, now we are able to get the expressive power of the isomorphism test. So now we are able to make the actual connection between the WL1 test and the previous GIN. So WL test could be formulated as like this, right? Considering neighbor and self representation, and we concatenate and get some using the hash. We provide the new color ID. We assign to as a sort of the embedding for the next layer. So for the next iteration, we use this label for the another hashing function. So that was the WL1 test, and the paper proved that this is actually the same capability in this function. So the functional formula is very similar, right? They're considering the self-representation and self color and the neighbor's color, assign a new ID, and it is used at the another iteration. Here, that information used in another layer. That is the difference. So difference is the hash function is used in the MLP. So that is the difference, and we use this for the injective property. Alright, so when you see the result at the table, the GIN based result shows consistent improvement in the most of the data set. So in particular, when you see this, the RDT in the data set, the mean MLP and GCM paper is getting a very bad result. So we are able to say this is almost failed in the learning, but we still getting the better result, and it's learning something. So we are able to see that the expressive power is helpful for the node classification task here. All right. So so far we have talked about the GIM paper, how the expressive power is related to the isomorphism test. After the paper, we have multiple advances recently to improve the existing GNN and GIN. The first example is identity-aware GNN. So it is designed to distinguish several the failure cases of GCN and GNNs. And one of them is that when the nodes who reside in the D regular graphs of different sizes, we are not able to identify the difference. So D regular graph means that each node has the same number of the neighbors. So in this case, 4 regular graphs, and we have 4 different neighbors per all nodes. So in this case, even though we have the same 4 regular graphs, the existing GCN is not able to identify each other. And when they have different sizes of the nodes, they are also not able to identify the difference. So they proved that, and they showed the solution. And also at the same time, when they have same neighbor structure but different shortest path distance, so it could be possible, right? So their proposed, the IDGNN is able to distinguish the nodes. We have several more advances. First one is that the distance encoding based GNN. We also sometimes we need to preserve the shortest distance between nodes and generalize paging scores, but when we learn GCN and GNN, we lose the distance measure across nodes. So we try to preserve that information in the GNN, and we also we also need to learn cycle graphs sometimes. For example, we are interested in the cyclic graph with the skip links of length L, and by using GNN we try to predict this R. So existing GCN and GNN is not able to do that, and the relation pooling GNN make that possible. And we also sometimes need to preserve positional information. This is the example. The A and the V1 and V2 has the exactly same neighborhood, right? The structure wise they're very similar. So he has two neighbors, they have the triangle, and they consider the subgraphs, the subtrees, and looks very similar. But they actually consider the position information in this case for the V1, to consider the distance between the V3 and V4. Between the V1 and V3, we get their distance is 1, so just 1/2 away. Distance between V1 and V4, we have 2. Between V2 and V3, we have 2. Between V2 and V4, we have 1. So we have different distance vector. So we are able to see they are different, and they try to preserve this information in their proposed GNN. But the existing GNN GCN fails to distinguish different nodes because they have the structurally similar, structurally equivalent. So they try to utilize this distance information in their GNN. They proposed a new GNN structure. And also we can count some subgraphs, and you can see the paper. So as you see today's class, so GNN's the expressive power is much limited. So depending on your own purpose in your task, some properties are more important to capture. For example, in here, shortest path and page rank and position. So depending on your choice, you can choose the proper ones. If there aren't, and you can propose your own GNNs. All right. Thank you for your attention, and see you next week. Bye bye.